Hello and welcome. This is a very interesting problem where there are two rigid tanks, each having a volume of 50 meter cube, are connected. One contains very cold air at 5 degrees Celsius, saturated, 100% relative humidity, and one relatively warmer air, also at 100% relative humidity. Now suppose we connect these two chambers and wait until they equilibrate. We don't allow any heat or work transfer. So finally, as you can realize, when the equilibrium is reached, the air temperature is going to be less than 20 degrees Celsius because this is at 5, this is at 20. We expect the final temperature to be lower than 20. And if the temperature is lower than 20, some water vapor is going to condense out. So we are asked to find the final temperature, final pressure, amount of condensation, etc. So let's begin. As you can see, we have two subsystems in the beginning state 1 and state 2. And at the final state, we have a single state consisting of the two tanks together, like a one chamber. I already started the process solution to reduce the time for this video. So state 1 is our left chamber. The pressure is given to 100 kPa. The volume is 50 meter cube. Temperature is 5 degrees Celsius and RH is 100%. And that completes the calculation of state 1. That's enough information to find state 1 completely. Of course, velocity and height elevations are set to 0 in all states. For state 2, similarly, we have all the information. The volume is 50 meter cube again. Pressure is given to us as 100 kPa. By the way, it could be different, but in this particular problem, it happens to be the same. Temperature is given and relative humidity is 100%. Okay, what about state 3? For state 3, if you notice, we don't have sufficient information. What is given is the total volume must be volume 1 plus volume 2. The total mass of dry air must be dry air at state 1 plus dry air at state 2. And of course, we don't know omega. Let's forget it for the time being. And so, as you can see in this problem, we don't have. Of course, the final RH will be 100% in this joint tank because we have condensation. So relative humidity will be 100%. So we need one more piece of information. What is the closing condition? That the final temperature should be such that there has been no heat transfer. Just suppose we arbitrarily pick a temperature. Suppose we say, I just want to give an example. Suppose we say the final temperature is 10 degrees Celsius. It's 5 and 20. Our guess is, 10 degrees Celsius is the final temperature. We arbitrarily decide. Of course, then we can find the state. It shows the final pressure and all the other quantities are found. Well, with that belief, if we proceed, so it's obviously an iterative solution. State 4 is the H2O, the condensation, and condensate temperature will be same as T3 by default because of the final temperature. So therefore, we can find the enthalpy of water. Notice that I put P4 equals P1. If you put X equals 0, that also will produce very close to the same enthalpy, which is the standard in psychrometry. But because this TESTapp is capable of finding any kind of state very easily, a real life condition is the final pressure of water is same as the tank pressure, which is P. We should say the pressure should be probably P3 would be a better representation of the pressure. So you can see the enthalpy doesn't change much. Okay. In the process panel, we have state 1 and 2 as our beginning state, as you can see, because we have two subsystems. So we pick up these two states here. Both are moist air. The final states also, we have two states. State 3 is our final moist air state, and state 4 is our pure H2O state, as you can see from the dynamic diagram. We put work transfer to be 0. There is no work transfer. Notice we calculated a heat transfer. In other words, for the final temperature to be 10 degrees Celsius, 827 kilojoules of heat must be lost. We must cool the tanks to achieve 10 degrees Celsius. In reality, we are not cooling the tank. Q should be 0. If Q was 0, then we would have said we got the correct answer. So what are we going to do now? We can now go and change the gas temperature slightly a little bit higher. Suppose we say the temperature is not in state 3 that we decided the temperature was 10 degree. No, let's put it, let's say we say it's 15 degrees Celsius, still between the two limits. If we calculate that and super calculate to update everything, we come back to the process panel. Look, now we have to add heat. Q is positive to obtain 15 degrees Celsius. So as you can see, we can just guess, we can narrow down our choices in between. And I tried it already. When we tried 13.5, you will find we reach pretty close to, this is almost very close, but you can see that we can go towards zero heat transfer by adjusting that final temperature. In other words, in this kind of problem, when you have to iterate between different states and the process equations, sometimes you have to guess the answer until a condition is met. That allows TEST to be a very powerful app to solve complicated problems.